Hello, brilliant learners. Imagine performing a chemical reaction in your school lab, not in a rigid sealed container, but in an open test tube, at constant atmospheric pressure. Previously, we learned that the heat absorbed at constant volume equals the change in internal energy, which is delta U equals Q sub V. But guess what? Most real chemical reactions don't happen in sealed volumes, but rather at constant pressure. So, we need a new way to understand heat in these circumstances. The key relation you see here tells us that the change in internal energy, delta U, equals the heat absorbed at constant pressure, Q subscript P, minus the pressure times change in volume, P times delta V. The term minus P delta V represents the work the system does when it expands or contracts. This fundamental insight sets the stage for defining a very important thermodynamic quantity called enthalpy, our star topic today. So, can you pause and ponder? Why do you think most reactions happen at constant pressure rather than volume? Go on. Take 15 seconds to think about where these reactions usually take place and what this implies about the volume. Welcome back. Let's now delve deeper. By rearranging the earlier equation, we express the heat at constant pressure, Q subscript P, as the difference between the sum of internal energy and pressure-volume product at two states, initial one and final two. To make calculations easier, scientists defined a new function called enthalpy, denoted by H, which equals internal energy U plus pressure P times volume V, or simply H equals U plus PV. Derived from a Greek word meaning to warm, enthalpy conceptually represents the heat content of the system. This brings us to a magical relation that heat at constant pressure, Q subscript P, equals the change in enthalpy, which is H2 minus H1, or delta H. That means when pressure is constant, the heat absorbed or released perfectly reflects the change in enthalpy. Imagine you are cooking in an open pot. The heat you add changes the enthalpy of the ingredients. Now think and ask yourself, if enthalpy depends only on the state, what kind of function is it? Pause for 15 seconds and ponder over the nature of enthalpy as a state function. Fantastic to see you here again. Let's explore an important difference between heat and enthalpy. Think of heat, Q, as the journey energy that depends on how you get from point A to point B. Different routes might use more or less fuel, right? Similarly, heat depends on the path or process during a change. However, enthalpy, H, is like the destination. It depends only on your starting point and ending point, not on the route taken. This means that the change in enthalpy, delta H, is independent of how the system arrived there. This special property makes enthalpy incredibly valuable because it simplifies calculating heat changes. At constant pressure, the heat absorbed or evolved equals the change in enthalpy. So every time you measure how much heat a reaction releases or absorbs in an open lab, you are actually measuring delta H, an intrinsic property of the states involved. Let's pause and think. Why is it advantageous for chemists to work with state functions like enthalpy instead of path functions like heat? Take 15 seconds and reflect on this. Hello! Let's continue with the core relationship that's widely used in thermodynamics, the change in enthalpy, delta H, for a process occurring at constant pressure. Delta H equals delta U plus pressure times delta V. This formula shows how the enthalpy change depends not only on the change in internal energy, but also on the work done due to volume change at constant pressure. Think of it this way. When gas expands during a reaction, it does work against the atmospheric pressure. This work is accounted for by the P delta V term. Imagine blowing a balloon. The air you blow in increases its volume. This requires energy, right? So, enthalpy change includes that energy used to expand the balloon. Knowing this relation helps chemists and engineers accurately calculate energy changes in reactions and processes that involve gases or volume changes. Now here's a question to think about. If a reaction involves solids only, where volume change is negligible, what would be the relationship between delta H and delta U? Pause for 15 seconds and reflect on this. Welcome back. Gases make things a bit more exciting because their volume changes significantly during reactions. To understand these changes, we use the ideal gas law, PV equals nRT. Here, P is pressure, V is volume, N is the number of moles, R is the gas constant, universal gas constant, and T is temperature. Equations 5.9 show this applied to gaseous reactants and products respectively. By subtracting the reactants equation from the products, we get P times the change in volume equals the change in moles of gas times RT, written as P delta V equals delta N subscript G times RT. Here, delta N subscript G is the difference in moles of gaseous products and reactants. This connection is essential because when the number of gas moles change, the volume changes too, affecting the enthalpy change of the reaction. Now, question your understanding. If no gas is involved in a reaction, what happens to the P delta V term? Think about it for 15 seconds. Let's tie everything together. We took the general enthalpy equation, delta H equals delta U plus pressure times delta V, and substituted P delta V with delta N subscript G times RT from the ideal gas law. The result, seen in equation 5.10, is a neat formula. Delta H equals delta U plus delta N subscript G times RT. This equation is a lifesaver when calculating enthalpy or internal energy changes in reactions involving gases. The term delta N subscript G captures the change in moles of gaseous reactants and products, and RT brings in the universal gas constant and temperature. So, the difference between enthalpy and internal energy changes depends on how gases are produced or consumed. Quick challenge question. If a reaction produces more gas molecules than it consumes, how would delta H compare to delta U? Take 15 seconds, think it through. Hello, dear students. Let's solve a real thermodynamics problem from problem 5.5. Calculate the internal energy change, delta U, when 1 mole of water vaporizes at 1 atmosphere bar pressure and 100 degrees Celsius. We know the enthalpy change, delta H, is 41 kilojoules per mole for this process. Remember our important relation from equation 5.10. Delta U equals delta H minus delta N subscript G times R times T. When water vaporizes, liquid water becomes 1 mole of water vapor gas, so delta N subscript G equals 1 mole. Substituting values, R, the gas constant, is 8.3 joules per mole Kelvin, and temperature T is 100 degrees Celsius plus 273, which equals 373 Kelvin. Calculating the correction term delta N subscript GRT gives us approximately 3.096 kilojoules per mole. Finally, subtract this from the enthalpy change of 41 kilojoules per mole, yielding an internal energy change of approximately 37.904 kilojoules per mole. Isn't it satisfying solving such problems? Before moving on, can you think, what would happen to internal energy change if water vaporized at a different pressure or temperature? Pause for 15 seconds and reflect. Welcome back. Let's clarify 2 essential concepts: extensive and intensive properties. Extensive properties, such as mass, volume, and enthalpy, depend on the quantity of matter in the system. If you have double the amount, these properties double. Conversely, intensive properties like temperature, pressure, and density remain unchanged regardless of how much substance you have. For example, looking at figure 5.6, you see a gas occupying volume V at temperature T. If we divide this container using a partition into two halves, each half now contains volume 5/2, meaning volume, an extensive property, changed because it depends on the amount of gas. However, the temperature, an intensive property, remains exactly the same in both halves. Additionally, chemists use molar properties to express extensive variables per mole. This helps compare properties independently of sample size. Before moving on, let's pause and ask, can you think of everyday examples of extensive and intensive properties? Take 15 seconds and make a quick mental list. Hello, eager learners! Imagine heating water on a stove. The heat you supply causes the temperature to rise. This change in temperature, delta T, is proportional to the heat transferred, Q, multiplied by a constant called heat capacity, C. Heat capacity depends on the amount of substance and its nature. Water, for instance, has a high heat capacity, meaning it requires lots of energy to increase its temperature even slightly. When we talk about heat capacity per mole, it's called molar heat capacity. Per unit mass, it's called specific heat. The mathematical relationship, written as equation 5.11, is Q equals C times M times delta T, or equivalently, C times delta T. Here, C is specific heat, M is mass, and C is heat capacity. This relation helps engineers and scientists calculate energy needed for heating or cooling materials. Now, a quick mental exercise. Why do you think metals have lower heat capacities than water? Pause for 15 seconds and think about the atomic structure and bonds involved. Greetings! Let's explore heat capacities in gases. At constant volume, the heat added to an ideal gas, Q subscript V, equals the heat capacity at constant volume, C subscript V, times change in temperature, delta T, and this equals the change in internal energy, delta U. At constant pressure, heat added, Q subscript P, equals heat capacity at constant pressure, C subscript P, times delta T, and equals the change in enthalpy, delta H. Using these relations, equation 5.12 presents that delta H equals delta U plus R times delta T, where R is the universal gas constant. Rearranging gives us equation 5.13, C subscript P minus C subscript V equals R. This means it always takes more heat to raise the temperature of gas at constant pressure than at constant volume because the gas expands doing work. Think about inflating a balloon with heat. You spend energy expanding it, not just raising temperature. Here's a question. Can you imagine why heating a gas in a sealed container, constant volume, uses less heat than heating it in an open container, constant pressure? Pause for 15 seconds and visualize this scenario. Hello, curious minds! Measuring energy changes during reactions is crucial for understanding chemical behavior. Calorimetry is the method scientists use to do this. A calorimeter is a device where a reaction occurs, and it is surrounded by a liquid with known heat capacity. As the reaction occurs, heat is absorbed or released, changing the temperature of surrounding liquid. By tracking this temperature change, we can precisely calculate the heat evolved or absorbed by the reaction. There are two main scenarios to measure heat: constant volume and constant pressure. Reactions carried out in a sealed container measure Q subscript V, while those open to atmospheric pressure measure Q subscript P. Using suitable calorimeters for each case, scientists unlock insights into enthalpy and energy changes. Let's take a second. Can you think of real-life situations where knowing heat change is important? Pause 15 seconds and brainstorm. Welcome! Let's dissect the bomb calorimeter, a marvel for measuring internal energy changes. You place a sample inside a strong steel container called the bomb. Oxygen is pumped in at high pressure, ensuring complete combustion. When you ignite the sample electrically using firing leads, it burns in an oxygen-rich environment. The bomb is immersed in a water bath, and as the sample combusts, it transfers heat to the water, raising its temperature. The thermometer monitors this change. Because the bomb's volume stays constant, no external work is done, making Q subscript V equal to delta U, the change in internal energy. This setup is widely used to find energy from fuels and foods. Think about this. Why do you think oxygen under pressure is essential in the bomb? Pause for 15 seconds and consider. Hello, energetic learners. Now let's look at measuring enthalpy change using a simple calorimeter. This consists of a foamed polystyrene cup that acts as an insulating vessel to minimize heat loss. Inside, the reaction mixture where the chemical change happens is placed. A thermometer inserted monitors temperature changes during the reaction. Because the cup insulates well, almost all heat evolved or absorbed by the reaction alters the mixture's temperature. This temperature change then helps us calculate the heat at constant pressure, denoted Q subscript P, which equals the enthalpy change, delta H. This setup is very useful for reactions in open containers, like most everyday chemical processes. Now, a quick thought. Why is foamed polystyrene a good choice for insulation in calorimeters? Take 15 seconds to consider. Hello, future scientists. Let's now apply what we've learned. In problem 5.6, 1 gram of graphite burns inside a bomb calorimeter at 298 Kelvin and 1 atmosphere pressure. The temperature of the calorimeter rises by 1 Kelvin, from 298 Kelvin to 299 Kelvin. The calorimeter has a heat capacity of 20.7 kilojoules per Kelvin. Using the formula Q equals C subscript V times delta T, we find the heat absorbed by the calorimeter is 20.7 times 1 equals 20.7 kilojoules. Since the calorimeter absorbs heat released by the reaction, the system loses 20.7 kilojoules, so delta U equals minus 20.7 kilojoules for the gram of graphite burned. Converting to moles, given graphite's molar mass is approximately 12 grams, delta U per mole is minus 248 kilojoules. Because the number of moles of gases does not change, delta H equals delta U, also minus 248 kilojoules per mole. This shows the reaction is exothermic, releasing energy. Think it over. Why is it important to know whether a reaction is exothermic or endothermic? Pause 15 seconds and reflect.